Hello students, in the last class we discussed about magnetic lines of force and comparison of magnetic field and electric field. Now we are going to discuss an important topic, Gauss law in magnetism and terrestrial magnetism. There is a chance to get 3 marks question from this topic, so please listen and try to make the notes. Today's first topic is Gauss law. Gauss law in magnetism. Gauss law in magnetism. Before going to start this Gauss law in magnetism, I want to explain Gauss law in electric field or electrostatics. What is the meaning? What it says? Gauss law gives the concept of electric flux. What is meant by electric flux? Electric flux. I will write the formula. Electric flux. What is meant by electric flux? The number of electric lines of force passing through unit area in perpendicular direction. Unit area in, so this symbol is perpendicular, in perpendicular direction. The number of electric lines of force passing through unit area in perpendicular direction is called electric flux. How it is defined? Sir, assume I kept a source of electric field, so electric field lines are passing here. This is the area. Sir, here we have to consider area. Through this area, the electric field and area vector must be perpendicular. See, electric field and area perpendicular, area vector always perpendicular to the area. This is A bar and E bar. This is the condition we will, in this case we can calculate phi is equal to E bar dot A bar. This is the formula. If you consider a small area, closed integral we can take. Closed integral of D bar E bar dot E bar dot A bar. Closed integral indicates that we have two limits are there. Line difference between closed integral and line integral. If you integrate any expression between the limits, that is known as closed integral. If you integrate any expression without limits, that is known as line integral. So here taking closed integral means we can take the limits. So here, if area is making an angle like this, if the area is like this, area is making an angle with the electric field, then we have to consider component of area in the direction of electric field. I can write here A cos theta is the component of area. It is perpendicular to the electric field. So while we are calculating the flux, the electric field and area vector or area, please try to remember one more time, electric field and area must be perpendicular to each other. So this is the concept of electric flux. So in this case, Gauss has given a condition. Instead of doing all these things, the Gauss given that if you consider any area, this is the calculation of electric flux by conventional method. Gauss given the statement, the total electric flux linked with the closed surface is equal to, what is the statement of Gauss law in electrostatics? The total number of, this is Gauss law. Gauss law in electrostatics, the total number of electric flux linked with a closed surface is equal to total number of electric flux linked with the closed surface equal to 1 upon epsilon naught times of total charge enclosed in it. That means we can write, assume this is a closed surface. In this closed surface, when we are taking the total charge is a scalar quantity, we have to mention the sign also. If you consider this is a plus q1, this is minus q2 plus q3, like these 3 charges are there. Now total flux phi is given by the formula 1 upon 4 pi epsilon naught total charge q1 plus q2 minus q3. This is about Gauss law in electrostatics. Now assume This is Gauss law. Gauss law in electrostatics. Gauss law in electrostatics. This is electric flux and Gauss law in electrostatics. How we can define Gauss law? Sir, what is Gauss law in electric fields? I can write now. This is recapitulation of Gauss law in electrostatics. Now we are going to study Gauss law in magnetism. The total number of magnetic flux linked with a closed surface is 0. This is about Gauss law in magnetism. What it is, I will explain you. The total number of magnetic flux linked with a closed surface is 0. Sir, why it is 0? I will explain you. Sir, in the same manner, Gauss law in electrostatics, closed integral E bar dot ds bar. How much you will get? We will get 1 upon 4 by epsilon naught times of Q enclosed. Here Q enclosed. If you apply the same formula, assume this is a surface, this is a closed surface, magnetic field like this. Magnetic field lines are like this. I am going to consider a elemental area ds. Now, in this case, if you apply this field, I will write closed integral b bar dot ds bar. If you apply b bar dot ds bar, I can write, actually this is the formula, epsilon naught into net pole strength. Net pole strength, epsilon naught net pole strength. Enclosed in it. Net pole strength enclosed in it. Sir, we assume net pole strength enclosed in it. What it means? Sir, assume I am going to consider this elemental surface. In this a dipole I placed. Sir, I already mentioned, if you consider a dipole, if you consider a magnet, it has two poles. What they are? North pole as well as south pole. Monopoles do not exist. So, if you consider a magnet, whatever may be the size, it has two poles. This is north pole, south pole. I already mentioned north pole is mentioned as plus positive charge. North pole is mentioned as positive charge. South pole is mentioned as negative charge. So, north pole strength plus m. South pole strength minus m. Now, if you apply this condition, closed integral b bar dot mu naught into m minus m. Why? North pole has pole strength plus m, south pole has pole strength minus m. So, these two gets cancelled. This is 0. So, this is the proof. The total number of magnetic flux linked with a closed surface is 0. What it indicates? It indicates that no monopoles do not exist. If you consider a magnetic surface, if you consider a magnet in a closed surface, it has two poles. So, a positive pole and negative pole. So, that means north pole, we can get north pole is taken as a positive, south pole is taken as negative. So, net pole strength becomes 0. As a result, net magnetic field over a closed surface is 0. This is the statement of Gauss law. Or we can say, if we consider any arbitrary surface in the NCERT textbook, this is the explanation they gave. Assume. We can say entering flux equal to leaving flux. Then what is the total flux linked with this? Assume this is a closed surface. This is a closed surface. No charge is placed here. Assume 1, 2, 3. 1, 2, 3. 3 lines are entered, 3 lines are leaving. Then what it is? Entering flux equal to leaving flux. What is the net charge enclosed in it? 0 only. So, net charge, no flux linked in this surface. So, whenever entering flux equal to leaving flux, then also net electric field is 0 or net magnetic field is 0. Based on this concept, they explained. Whatever the explanation, both are same. If you consider a closed surface, number of flux entering equal to number of flux leaving, then also net electric field or net magnetic field also 0. Now, this is about Gauss law in magnetism. Now, we are going to discuss terrestrial magnetism. Terrestrial magnetism. Terrestrial magnetism. What is meant by terrestrial magnetism? Terrestrial indicates that big size. The magnetism exhibited, the branch of physics which deals with the magnetism exhibited by Earth's surface is the study of magnetic field exhibited by Earth's surface is known as terrestrial magnetism. I will write the definition. The study of magnetic field, magnetic effects, the study of magnetic effects produced by Earth, magnetic effects produced by Earth is called terrestrial magnetism. You may have a question that why Earth acts as magnet. First I want to explain. There are so many times scientists explain in different methods. I will explain those things step by step. Instead of knowing the scientist name, please try to understand what they know. First they said that, Williams, I think so. William explained that Earth contains a huge amount of magnetite ore in its crust. This is the responsible for magnetism. After the study, Earth do not contain large amount of magnetite. It contains a minor amount of magnetite. So his explanation is wrong. Next, what they said. One more scientist said that Earth is surrounded by magnetic shields. After doing a number of experiments, they also said that it is not surrounded by any magnetic shield. Now, finally, American scientists said that yet in the Earth crust, temperature is high, about 300 from the center, from the surface, about 3000 kilometers. The temperature is high, so no solid state materials exist. All the matter in the form of molten state. That means like a semi-liquid. If you take a solid, if you heat, what will happen? We can get a molten matter. That is known as molten state. So no matter exists in the form of solid. So this molten state, at the molten state, all the substances are in the form of ions. So due to rotation of Earth, these ions are in motion. So whenever a charge, this molten mass produce a electric current. What is meant by current? Motion of charged particles. Here a molten mass, it do not have any bonded atoms. It has ions. Ions are there. These ions in rotation. What is meant by charge? Electric current. Motion of charge is known as current. So this moving charges, molten state matter contain, what it contain ions. Ions are in motion. These moving ions produce motional currents. So these motional currents are responsible. We know already in moving charges and matter, a moving charge produce electric field as well as magnetic field. So these moving charges are responsible for the production of magnetism. So this is the one of the legible explanation for magnetism exhibited by Earth. So what is the reason to show Earth magnetism is Earth acts as a magnet because it has molten mass. This molten mass contains only ions. Since due to rotation of Earth, these molten ions also rotation. Ions in rotation produce current. These currents are responsible for the production of magnetism. So this is the this is molten mass is responsible for the exhibition of magnetism by the Earth's surface. Now we are going to discuss some definitions. These are very, very important. It will help to understand the terrestrial magnetism in detail. So what are the definitions we are going to discuss now? Assume this is the Earth's surface. Okay. This is assume North Pole. This is North Pole, this is South Pole. A line passing through North Pole and South Pole is known as magnetic axis. I will write the definitions in detail. First, magnetic axis. Geometric axis. First definition is magnetic axis, geometric axis. geometric axis, geometric meridian, geometric meridian, magnetic axis, magnetic meridian. These are the things first we want to discuss. What is meant by magnetic axis? A line passing through North Pole and South Pole is known as magnetic axis. Sorry. A line passing through North Pole and South Pole is known as geometric axis. About geometric axis, Earth is rotating. So, what is the definition of geometric axis? A line passing through North and South Pole of Earth. A line passing through North and South Pole of Earth is known as geometric axis, about which Earth is doing the rotation. Next, come to the geometric meridian. What is meant by meridian? A plane, whenever the meridian has come in our mind, meridian always indicates plane. What is the meant by meridian? Meridian indicates the plane. A plane which contain, assume this. So, if you assume this is a plane like this, try to assume this is the axis. This kerchief act as a plane. A plane which contain magnetic north and magnetic south is known as magnetic meridian, like this. Sorry, a plane which contain geometric north and geometric south is known as geometric meridian. Geographic meridian or geometric meridian, anything is right, so there is no wrong. Geographic, or we can write geometric meridian, geographic axis, geometric axis, all are same, so don't confuse. Or geographic axis, geometric axis, both are same. Geographic meridian, geometric meridian also same. So here what it meant by meridian? A plane containing geographic axis. A plane containing geographic axis is called geographic meridian. This is the definition of geographic. Now we are studying, this is known as geometric axis. I am going to write GA. Now if you consider, by the experiments they revealed that the magnetic axis and magnetic axis of Earth and geometric axis of Earth are, what is meant by magnet? I already mentioned. Sir, if you observe, we can treat Earth contain a huge amount of magnet like this. This is the magnetic axis. Here I will write. Please try to understand. Here in NCERT textbook they will give NM and SM. I will explain in detail. I am going to rub these things. Sir, we know that this is the axis about which Earth is rotating. This is geometric axis. Now, sir, we know, I already mentioned, like poles repel each other, unlike poles attract each other. So a freely suspended magnet comes to rest in north and south direction. Sir, here in magnet needle, assume this is the magnetic needle. Magnetic needle come to rest. The pole which faces towards the geometric north is known as north pole. A pole which shows toward the geometric south is known as south pole. Sir, here if you, this is a magnetic, this is NM, SM. SM and NM are the north pole of magnet, south pole of magnet. SE is the south pole of earth, NE is the north pole of earth. See here, we know like poles repel each other, unlike poles attract each other. So north pole of the magnet will come to rest in this direction. So north pole is attracted by south pole of earth only, no. So here south pole of earth attracts north pole of magnet. In the same manner, north pole of earth attracts south pole of the magnet. So in NCERT textbook they will give NM. NM indicates north pole of the magnet. Here NM indicates the north pole of the magnetic needle. North pole of the magnetic needle is attracted by south pole of earth. South pole of magnetic needle is attracted by north pole of the earth. So don't get confused. Here a line passing through magnetic south and magnetic north is known as magnetic axis. Here I will write. If you consider this a line passing through magnetic axis and magnetic south and magnetic north is called this is magnetic axis. I will write the definition of magnetic axis. A line passing through magnetic north and south pole of earth. A line passing through magnetic north and magnetic south pole of earth. South pole of earth is called magnetic axis. Now magnetic meridian. What is meant by magnetic meridian? A plane which passes through which passes through magnetic axis. A plane which contain, or we can better write this word, which passes through, not good, which contain. A plane which contain magnetic axis is called magnetic meridian. I will write a circle magnetic equator. What is meant by magnetic equator and geometric equator? I will explain. A circle which is perpendicular to geometric axis is known as geometric equator, GE. A circular plane which is perpendicular to geometric axis is known as geometric equator. I will write that also, equator. Two more definitions. We are discussing 6 definitions. I will revise one more time. Geometric equator, geographic equator, geographic equator. What it is? A plane, a circular plane. Better to write in detail. A circular plane perpendicular to geographic axis is called geographic equator. In the same manner, magnetic equator. Magnetic equator, a circular plane perpendicular to magnetic axis. A circular plane perpendicular to magnetic axis is called magnetic equator. We don't have much things about equators. Please remember geometric axis. I am going to repeat one more time. We studied 6 definitions. What they are, I am going to repeat. What is meant by geometric axis? A line passing through geometric axis is a line passing through geometric north to geometric south is known as geometric axis. A plane containing geometric north and geometric south or geometric axis is known as geometric meridian. In the same manner, sir, earth acts as a bar magnet. Here the earth magnetic axis is not along the geometric axis. The magnetic axis of earth is inclining at an angle of 13 degrees 11 degrees 3 minutes. So this angle here the magnetic axis and geometric axis are inclining at an angle of 11 degrees. So here a line passing through magnetic south or magnetic north is called magnetic axis. A plane containing magnetic axis is known as magnetic meridian. These 4 definitions you have to understand. Now if you understand these definitions, I am going to explain the 3 definitions. In order to define a magnetic field at a particular place, we need 3 terms. These are known as elements of earth magnetic field. I will write the definition. To define a magnetic field, at a particular point on the earth's surface. To define magnetic field at a particular point on the earth's surface, we need these 3 terms. First, magnetic declination, next angle of dip, horizontal component of earth magnetic field. These are the 3 things we have to understand. Once again I am repeating. To define magnetic field at a particular point on the earth's surface, we need these 3 parameters. What they are? First parameter magnetic declination, next angle of dip, next horizontal component of earth magnetic field. Sir, I am going to define these terms. First, magnetic declination. What is the definition of magnetic declination? The angle between GM. GM means geometric meridian. Please try to understand GM and MM. The angle between GM and MM. What is meant by GM? GM indicates the geographic meridian. mm indicates the magnetic meridian. Okay, sir, please look at the board. What is meant by meridian? A plane which contain, assume this is a plane ABCD. The plane ABCD, this I am going to write as mm, magnetic meridian. The angle between magnetic meridian and geometric meridian, assume this is a plane. This is a plane A dash B dash. The plane A dash B dash, this plane is known as GM, geometric meridian. A plane ABCD is magnetic meridian. A dash B dash equal to geometric meridian. The angle between magnetic meridian and geometric meridian is known as angle of declination. This is theta. We can write this is theta. This theta is the angle between geometric meridian and magnetic meridian. Once again writing, magnetic declination is the angle between geometric meridian and magnetic meridian. So this is the ABC is the magnetic meridian. This is the geometric meridian. Angle between these two is known as angle of declination. So here magnetic declination or angle of declination, we can write theta. Angle of declination, angle of declination, angle of dip, or we can say inclination. So this is about angle of declination. Angle of declination is the angle between geometric meridian and magnetic meridian. So I am going to rub these things. Next, one more definition I am going to write, angle of dip. Sir, assume here I am keeping a magnetic needle. I am taking a magnetic needle like this. This is a horizontal circle. This is a ring like this. This is the vertical surface. To this vertical surface, a needle is present like this. To the vertical surface, a needle is present. This needle is free to rotate. So if you suspend a free needle, it will tilt. Here I will take like this. This is a vertical plane. On the vertical plane, this needle is free to rotate. Assume this blue end is north pole, white end, assume this is north pole, this is south pole. So if I suspend this ring like this, it will point. It will come to rest about some particular point. Assume like this. This is north, this is south. The head of the north pole is come to rest in a particular at a particular point in the magnetic field. That particular point here, the angle between magnetic meridian and the resultant magnetic field. This north pole where it points, that is the resultant magnetic field BE, or I can write BR. At this point where the magnetic needle come to rest, that is the direction of magnetic field at that particular point. So the magnetic field not come to horizontal direction, not come to vertical direction at a particular point. At poles and equator only this is possible. So if it is not at poles, not at equator, means it not come to rest. So if we consider the magnetic needle come to rest at a particular point. So this particular the direction in which the magnetic needle come to rest, that indicates the resultant magnetic field at that point. So I will write angle of declination. If you consider this is a needle, like this it is, a needle is there. This is a dip circle, we can say this is a dip circle. This indicates 90 degrees, this indicates 0. So with respect to horizontal, it makes an angle delta. This is dip circle. This is used to find dip at a particular place. Dip means resultant magnetic field at a particular place. Sir, angle of dip. A freely suspended magnetic needle comes to rest at an angle delta with respect to magnetic meridian. A freely suspended magnetic needle come to rest at an angle delta in magnetic meridian. The arrow points the arrowhead, that is north pole. The arrowhead direction indicates direction of resultant magnetic field. At that point, at that place. This angle keep on changes from place to place. So if you assume this is the magnetic needle, the magnetic needle comes to rest at a particular point in the magnetic needle comes to rest at a particular point. The direction in which the north pole of the needle shows, that is the resultant magnetic field. So this resultant magnetic field, I can resolve, this is the resultant B. I can resolve this B into two components. So if you resolve this B into two components, C is the magnetic meridian. In this magnetic meridian, this is the resultant magnetic field. The resultant magnetic field makes an angle delta with the horizontal. If you assume to this plane, this is horizontal, this is vertical, I can resolve this B into two components, BH. B horizontal component, B vertical component. So BH is equal to B cos delta, BV is equal to B cos delta. The horizontal component of resultant magnetic field at a particular place gives the horizontal magnetic field. BH is the component of resultant magnetic field along the horizontal direction. I will write. The magnetic needle comes in this direction, rests in this direction, north pole in this direction. BH, horizontal component of magnetic field. Horizontal component of magnetic field indicates that the horizontal component of resultant magnetic field at a particular position. The horizontal component of resultant magnetic field. Horizontal component of resultant magnetic field. Resultant magnetic field at a particular place. The horizontal component of resultant magnetic field at a particular place is known as horizontal component magnetic field, and it is written by the formula BH. Sir, if you go for different places, some places it is delta, sometimes it is phi. but the vertical component of resultant magnetic field do not change. Horizontal component of magnetic field keep on changing with respect to place. We will discuss that later. Here if you consider in this case, this is a resultant magnetic field, it makes an angle delta with the horizontal direction. This is B horizontal, this is B vertical. If you resolve this B into two components, we can get B cos delta, B sin delta. BH is equal to B cos delta, BV is equal to B sin delta. So this is equation 1, this is equation 2. 2 by 1, write 2 by 1, then what we will get? Tan delta. Sir, I will write one more step. 2 by 1. I am writing 2 divided by 1. So what we can get? B sin delta by B cos delta equal to BV by BH. BV by BH. BB gets cancelled. Tan delta is equal to BV by BH. That implies delta equal to tan inverse BV by BH. If you find tan inverse BV by BH at a particular place, we can get the angle of dip at a particular place. So today's class is completed. Tomorrow we can discuss magnetic properties of the materials.